In this lesson, we'll review the short-term working memory system, the long-term memory system, both episodic and semantic memory, as well as what happens when we reactivate a memory when we imagine things. Now, the human brain is made of 80 billion neurons or thereabouts, and we're looking at the left hemisphere here. The surface of the left hemisphere would be the cerebral cortex. We have the temporal cortex here. The hippocampus is underneath the temporal cortex, and it's an important structure in making episodic memories, long-term memories. It's also the gateway to making semantic memories as well. And in the frontal cortex, we have brain systems that we're calling the working memory system, a short-term memory system. Now we have the eyeball here, and so the brain is observing a roaring tiger. So visual information will be sent to the visual cortex, and a certain subset of cells will be responding to the visual appearance of the tiger. And here we have them in green. Now, because we're currently seeing the tiger is going to be in our working memory. And the idea is the visual system, those cells that were activated by the tiger, are going to be sending their electrical signals to the frontal cortex regions. And in fact, loops of neural activity will be established as long as we're looking at the tiger. Well, the tiger might also be roaring, so we're hearing the tiger. We have auditory cortex here in the temporal cortex, so the orange cells would be responding to the roar of the tiger, and again setting up loops so that we're perceiving the roar as well. So we've got the contents of our working memory is a roaring tiger, but in addition, both the visual and auditory systems are sending information to the hippocampus. So those two perceptual qualities will be linked by the hippocampus, and we're forming then an episodic memory of this observation of the roaring tiger. And that's indicated by these cells in the hippocampus with strong neural connections between them. Now, we've learned that the hippocampus is making episodic memories, which includes the circumstances of learning, the details of the learning situation, not just the characteristics of the tiger, what it looks like and what it sounds like. Also in the cortex then, in addition to the cells responding to the appearance of the tiger and the neurons responding to the sound of the tiger, we have other neurons that are linking those two sensory qualities. These pink cells are in a region of brain called association cortex. They respond to both visual stimuli and auditory stimuli, and scientists argue that these kinds of cells can link together what a tiger looks like with what a tiger sounds like, and these populations of cells will be the future concept of a tiger. So in this situation of observing some object in the world, we are using our short-term memory system because that object will be the contents of our working memory, but we also have the capacity to make a long-term memory of that observation. So whatever is in our working memory has the potential to be stored as a long-term memory by way of the hippocampal system. Now, after the observing event, then when the tiger goes away, we're left then with an episodic memory trace in the hippocampus, but as well we have memory traces in the cortex, because after all, the cortex was processing the visual and auditory qualities of the tiger. But notice, we're showing that the hippocampal memory trace is a strong memory trace with solid lines here, and we're indicating that the memory traces in the cortex are weaker with dashed lines. It should also be noted that the memory trace for the tiger experience involves just a subset of cells in the visual cortex, just those that were responding to the tiger. So the visual system has many neurons, and when we see a particular object, not all of the neurons are going to be responding to that particular object. So at this point, we can identify these neurons as sort of tiger neurons. The preferred stimulus that would activate these neurons is a tiger. And likewise over here, the preferred stimulus would be the sound of the tiger. And again, the preferred stimulus of a neuron is just whatever stimulus that generates maximum electrical activity in that neuron. The observing event has, in a sense, tuned up or selected certain cells to be responding to the tiger. So we can sort of say that by observing the tiger, we have created neurons that will selectively respond to tigers. It's not that we were born with tiger neurons, it's that the learning event itself is going to cause neuroplasticity to occur, and these cells will become tuned up to become tiger cells. Now, later that evening, when we go to sleep, some interesting processing occurs when we are unconscious. So, scientists have discovered that the brain is reprocessing recently learned information. And the idea is that the hippocampus, with its memory trace of the learning event, the hippocampus will begin to signal the cortex. So there's a dynamic interaction between the hippocampus and those regions of cortex that were processing the learning event, in this case, seeing a tiger that was roaring. So the hippocampus, in a sense, is going to be helping the cortex to strengthen the memory traces of the tiger experience. And we call this memory consolidation. And in fact, that communication between hippocampus and cortex is going to help the cortical cells grow new synapses to strengthen the connections between those neurons that were activated by the tiger, including the neurons that are linking together the different sensory aspects of the tiger, the concept cells. So this will become the tiger concept. We can describe this process in the following way. It's as if the hippocampus is replaying the memory, right? But this time, sort of the hippocampus is driving the memory so that the cortical cells are going to strengthen their connections. Now, this idea of replay has experimental data behind it. So, in other words, scientists have been able to record hippocampal neurons when an animal's learning something, and what they find is those very same hippocampal neurons are reactivated during this sleep process. It's as if the hippocampus is replaying the memory so that the cortical memory traces can be strengthened. We should also note that it makes sense that the brain is processing recently learned information during sleep, because during sleep then we are unconscious, and so we don't have any ongoing perceptual activity that might be interfering with this memory processing. So sleep then provides a context whereby recently learned information can be worked on. The hippocampus will assist the cortex in strengthening those memory traces, and this is how we build up a semantic memory system filled with all kinds of information about our world. Now, the process of strengthening the cortical memory traces is how the contents of an episodic learning event can be integrated into semantic memory. So the hippocampal system is instrumental not just in making new episodic memories, but also then providing the content for semantic memory. So we'll be storing information about what a tiger sounds like and what a tiger looks like, as well as other facts we might have learned about tigers, like where they live and what they eat, etc. The episodic memory is related to the hippocampal memory trace. And we will need the hippocampus then to retrieve the detail and context-rich and vivid episodic memory. But even if we lose the hippocampus, if we have successfully completed memory consolidation, we will have integrated tiger information into our semantic memory. So here we see, after memory consolidation, the cortical memory traces are stronger now, the solid lines. So we have at this time we would have a strong memory trace in the hippocampus and strong cortical memory traces. So we would have both an episodic memory of the learning event and semantic memory of information about tigers. If somebody asks me about tigers, I can access my semantic memory and give them information about tigers. If somebody were to ask me to remember when I saw my first tiger, then I'm going to be engaging the hippocampal system to recreate a vivid episodic memory. Now, let's see what happens when we imagine a tiger. So the cue will be the cue to imagine a tiger. Now, somebody could say it, imagine a tiger, in which case the sound of the word tiger, which I have a memory trace in my auditory cortex, so I can recognize that as the sound of the word tiger. Well, that has been linked up to my concept of a tiger, so the sound of the word tiger will activate the concept of a tiger. Or the instruction could come by way of writing. I might read, imagine a tiger. Well, I have a memory trace of what the word tiger looks like, and that also is linked up to the concept of tiger. So whether it's through auditory or visual channels, I can activate the concept of a tiger. And when those neurons are activated, they will then correspondingly activate other memory traces that are linked to the concept. So I can activate what a tiger sounds like, and I can activate what a tiger looks like. And when these memory traces are activated, then now we're going to be retrieving what a tiger looks like and sounds like, and that information will enter into the working memory system. So in a sense then, the working memory system is able to interact with long-term memory. It can search long-term memory for relevant information that is related to the content of working memory. Now, what's the evidence that we engage memory traces when we imagine things? Well, teams that are using fMRI, for example, find that when we are seeing a tiger, of course, we activate visual cortex, but likewise, when we imagine a tiger, we are reactivating the visual cortex during imagination. And so this supports the reactivation hypothesis that we'll see in a moment, that the same areas of the brain that are used to process what a tiger looks like are going to be reactivated when we imagine what a tiger looks like. Now, we should note, though, that the level of activity when we imagine something is not as great as when we actually see the thing. So when we're imagining a tiger, we're reactivating some of the visual system to construct the image of a tiger, but the level of activity is not as great as when we're actually seeing a tiger. Most plausibly because we're not, if we're not seeing the tiger, then we don't have all those visual inputs to the visual cortex. So we have reduced activation of the visual system, but nevertheless, we're reactivating the visual system when we create an image of a tiger. And just a note about terminology, when we're imagining a tiger, we're in a sense activating the tiger neurons internally. When we're seeing a tiger, the tiger neurons are being activated externally from an external source. So perception is triggered by an external object in the world, but we can internally reactivate memory traces to imagine things, and that will be an internal reactivation. And when we successfully imagine a tiger, then what we're doing is we're creating loops of neural activity between tiger cells in the working memory system, and loops of neural activity between the auditory cells, the roaring tiger cells in our working memory system. And so we will be imagining a roaring tiger in our mind's eye, as it were. And so long as those loops are engaged, we will be imagining the tiger. When the loops stop, then the tiger will leave our imagination. So we call this the reactivation hypothesis, that those regions of the brain that were active when perceiving the tiger are going to be used to store memory traces of the tiger attributes, and then later we can reactivate those memory traces to imagine a tiger. And we also saw some direct evidence of the reactivation hypothesis in a film clip by Itzhak Fried, and they identified a hippocampal neuron that responded to a video clip of The Simpsons. Well, that same hippocampal neuron was reactivated when the subject was recalling what they saw a moment ago. And so this, again, is direct evidence of the reactivation hypothesis, that the cells in the brain that are used to perceive something and then store a memory of that something are reactivated later again when we retrieve a memory or imagine that object.